Hey, everybody. It's Wednesday, June 2nd. Hopefully, you had a nice Memorial Day weekend and a relatively easy time with yesterday's test. As you can see here in the aim today, our goal for today's video is all about discussing the Doppler effect, specifically how the Doppler effect can be used to track the motion of objects. Now, the first thing that we should say about the Doppler effect is that you've probably heard of it before. If we were in class, the first question that I would ask would be, have you ever heard of the Doppler effect before? And usually after everybody gets a while to think about it, somebody ends up saying, yeah, I think I've heard of it on the news. I know whenever I have the news on at 5 or 6 o'clock or whatever, they often cut to the weather person and they say, like, here's News Channel 4, Doppler weather radar. The Doppler effect is something in physics that happens with waves specifically that we can use to track the motion of objects. The Doppler effect is essentially the main physics principle that is applied to track the motion of storm clouds. Now, if you took earth science, you should know what the Doppler effect is. It's discussed in earth science. If you didn't take earth science, like I didn't take earth science in high school, that's fine. But even if you don't already know what the Doppler effect is, surely you've observed it before. Because we all live in a city where there are a lot of cars driving, I'm sure you've heard a car horn honking. And if that car horn was in motion, if you've ever heard a car honk its horn, like that car right outside my window just did, I don't know if you heard it. If you've ever heard a car honk its horn while it's moving, then you've observed the Doppler effect. Let's take a look at how that works. In this video here, this video is demonstrating the Doppler effect. So you can see the car down there. It's going to be approaching the person taking the video and then drive away from them afterwards. All credit to Physics Boy for filming this video. Here we go. All right, so hopefully you noticed the pretty drastic change in the horn sound in that video as it was first going towards the person and then passing them and driving away from them. That's what the Doppler effect is, or at least that's a demonstration of it. Now we have a very obvious question to ask, and that question is, what actually physically just happened? What just happened is a demonstration of the Doppler effect. And so if we ask ourselves the question, well, what is that? What happened? What is the Doppler effect? We come up with a pretty straightforward explanation. The Doppler effect is the predictable, apparent shift in frequency due to the relative motion between the source of a wave and the observer of a wave. So remember, the frequency of a sound wave, like a car horn, and we're going to address this in great detail here in a couple of minutes, but the frequency of a sound wave is its pitch. And so if you especially notice when the car horn is going away from the observer, you sort of hear it trail off like, it sort of lowers in pitch. It gets like a deeper sound. That's because the frequency of the sound is changing. And so the idea here is that because the source is in motion relative to the observer, there is a shift in frequency as observed by the observer. Now, I want to be very clear about that. Notice here I have this word apparent emphasized here in this slide. The reason why I say that is because we should be totally clear about this. The actual frequency of the wave is not changing, but it appears to be changing from the observer's point of view. And that's why we say it is the apparent shift in frequency due to the relative motion between the wave source and the observer. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so now from my point of view, trying to teach this to you over the internet, I have two options. The first option is to just give you a bunch of examples of the Doppler effect and ask you to memorize them, and hopefully you memorize them and then you'll know them. The second option, which I think is far superior, and that's why this is what we're going to do, is I can show you exactly how the Doppler effect works, why the observer thinks there is a different frequency of this wave than there actually is, and so on. And the way that we are going to do that is by making use of this simulator. I'll put a link for this simulator in the post for today. And this simulator and our observations using the simulator is going to be able to tell us everything we need to know about the Doppler effect. So as you can see here, the simulator has a spaceship and a star. The star here is what we are going to consider to be the wave source. Why are we considering the star to be the wave source? Well, because the star is emitting light waves. We know that light is a wave based on what we said earlier, and so this thing is a perfectly suitable example for a wave source. The other thing to note before we get started, let me see if I can make this red just so it'll be easy to see. The green lines here are the peaks of the wave, where the yellow lines are the troughs of the wave. And so what you're going to need to see here, although you will be able to see it down here, I think it's good to get a visual representation with these wavefronts here, is a wavelength of the wave is going to be measured as the distance from peak to peak. Now remember, we said we can measure the wavelength in a variety of different ways, but peak to peak is a pretty easy option. I'm going to erase these, so just remember green is a peak, yellow is a trough, and we'll see what happens now. I'm going to have the observer, or I'll have the source here to make it like the car horn. I'll have the star approach the spaceship, and we'll see what happens from the perspective of the spaceship. So I'm going to unpause this, and I'm going to have the star move in the direction of the spaceship. I want you to just watch for a second before I let this thing go, the steady pattern of waves that is being emitted. There is a constant frequency. Okay, now I hope what you notice here is that the fact that this source is moving toward the observer causes these wavefronts to bunch up. That's the key idea. If you didn't quite see it, I'll make it go a little faster just to make the effect more apparent. So notice now, because this thing is moving toward the source, we see a different distance between the peaks of the wave. Notice this line that I just drew between the two peaks is significantly shorter than this line. What that tells us, because again, the distance of the line is measuring the wavelength, is that the apparent wavelength here of this wave, at least from the perspective of this spaceship, got shorter. And that's because the star sends out a wave and then moves closer to that wave before it sends out another one. That's the idea. Now we'll see how that affects the spaceship's perception of the wave next. And now we have a pretty simple question to ask ourselves. If before the star started moving, the waves that reached the spaceship had this wavelength, and now that the star is moving, the waves that are going to reach the spaceship have this wavelength, what happened to the wavelength? If it's not obvious to you already, hopefully you should see it when it gets to the detector on the spaceship. That's what's being shown here by this little screen down here. Notice the wavelength is getting shorter. And now all we have to ask to drive this point home is, if the wavelength is getting shorter, then what's happening to the frequency of the wave? Well, the way we answer that is by using the equation for the speed of the wave. We have to ask ourselves the question, what is the relationship between the frequency and the wavelength? Well, if we solve this equation for frequency, which we do by dividing both sides by lambda, we get the frequency is equal to the speed over the wavelength. This is the time in class when I would usually ask the question, according to that equation, what is the mathematical relationship between the speed and the wavelength? And the answer is, because the wavelength is in the denominator, while the speed is constant. Remember, same medium, same speedium. This light is traveling in space, so its speed is what we call the speed of light in a vacuum, 3.00 times 10 to the 8 meters per second. Because the speed is going to be a constant number here, and the wavelength is in the denominator, the frequency is inversely proportional to the wavelength. So what we are saying here, the grand summary of all of this part of the video, is when the wave source and the observer move toward each other, the frequency measured by the observer goes up. And that's entirely due to the relative motion between the source and the observer. One more time, just to drive this point home, we got a constant wavelength. They start to move toward each other. The wavefronts bunch up, which means the effective wavelength got smaller. And because the effective wavelength gets smaller, or the measured wavelength gets smaller, the measured frequency gets bigger. When they move toward each other, the frequency goes up. Now, before we move on, I just want to make one point about the thing I just said a second ago, because I usually take the opportunity to say the conclusion slightly incorrectly to see if anybody notices, so we can drive this point home. And I'm going to write this in the notes afterwards. I'm going to summarize all of this stuff with a couple of notes here in a minute. What I just said, and you can go back and listen to it if you want, is when they move toward each other, the frequency goes up. That's actually slightly inaccurate. The frequency does not actually go up, but the apparent frequency does. It's important to realize this is only a result of the relative motion between the source and the observer. If there was another source that traveled alongside the star and never moved relative to the star, they would observe no difference. And that's an important thing to realize. This is only as a result of the relative motion between the source and the observer. The frequency doesn't actually change. What changes is how the observer measures the frequency. Okay, now let's do the opposite case. I'm going to reset this here. And as we can see, I'm going to pause this here for a second. As we can see, this thing is generating waves with a constant frequency and wavelength, and we can tell that by looking at the length of this line between all these peaks here, between all the green lines. We could do it between the troughs as well. It doesn't really matter. We can see here that these lines are evenly spaced. I hope that's pretty obvious to everybody. And now what we're going to see is what happens to the spacing between those lines, or in other words, what happens to the wavelength as measured by the spaceship as the source of the waves moves away from the observer. So I'm going to unpause this here. I'm going to let the star go the other way now. And I want you to watch what happens to the spacing of the lines. Notice here, they're constant. So unfortunately, this thing said it was too far for accurate measurements. So I'm going to see if I can move them around and fix that a little bit here on the back end. But the visual representation is all we need. And notice this was paused almost so that this red line that I had originally drawn there is still exactly lined up with these peaks. Notice, though, because the spaceship moved away, the wavelength, as perceived by the spaceship, got significantly larger. I think that makes a lot of sense, because the star sends out a wave, but then moves away and sends out another wave, and then moves away and sends out another wave. And so as a result, the space between those waves gets larger. And now we have to ask the question again, well, if the wavelength as measured by the spaceship got larger, well, what happened to the frequency? Well, we just go back to the wave speed equation. And the wave speed equation, as we went over a minute ago, says the frequency is equal to the speed over the wavelength. And if the speed is constant, remember, same medium, same speedium, then the frequency is inversely proportional to the wavelength. So as the source and the observer move away from each other, the wavelength gets bigger, so the frequency goes down. That's the idea. Now, the frequency, again, does not actually go down. It is just measured as being lower by the observer. It's an apparent shift in frequency. Now, I'm just going to try to do this one more time and see if I can get this to work out here. I'm going to try to get this to be a little closer and then get it to stop. Okay, yeah, that works. So I'll get it to go right here and then make it stop. We'll let that pattern of constancy of the waves come back. Notice here now we're seeing constant wavelength waves on the detector, and now we'll have this thing move away. Notice not only can you see it visually with the wavefronts, but you can also see it here on the graph. Notice now these things are getting spread out further and further and further. And so because the distance between the actual peaks on the detector is getting bigger, the wavelength measured by the spaceship is getting larger. And so the frequency as measured by the spaceship is getting smaller. All right, so let's go ahead and summarize what we just saw with that simulator. And I'd like to start here with the case of the source and the observer moving away from each other. This is actually the last one we just did. And so we'll say here, when the observer and the source are moving away from each other, the apparent wavelength of the waves gets larger as each wave is being emitted farther from the previous wavefront due to the motion. I want to just stop there for a second because I think that's a really helpful way to think about it. The spaceship or the star or whatever the source of the waves is doing, it's emitting a wave, it's moving away, and then it's emitting another one. So effectively, the waves just get spaced out more. That's how it works. And if the waves get spaced out more, then that effectively means, at least according to the observer, that their wavelength is getting larger. And of course, if the wavelength is getting larger, that causes a decrease in the frequency. So when the observer and the source are moving away from each other, the apparent wavelength of the wave gets larger, which causes a decrease in the apparent frequency. And what you really need to know here is that the apparent wavelength goes up and the apparent frequency goes down. Moving on, of course, the next case we want to discuss here are the source and the observer moving toward each other. And when the observer and the source are moving toward each other, the apparent wavelength of the waves gets smaller. And that makes sense based on what we said about the first case, because each wave is being emitted closer to the previous wavefront due to the motion. So this source sends out a wave, moves toward it, and then sends out another one. And so they start to bunch up, as hopefully you saw in the simulator. And because all of those wavefronts bunch up, then effectively, at least according to the observer, it appears as though the wavelength is getting smaller. And of course, if the wavelength gets smaller due to the inverse relationship between the wavelength and the frequency, that causes an increase in the apparent frequency. So to be totally clear, when the observer and the source are moving toward each other, the apparent wavelength of the waves gets smaller, which causes an increase in the apparent frequency. And so the thing you really need to know here is that in this case, the apparent wavelength decreases and the apparent frequency increases. And really simply put, like the thing you absolutely need to memorize is when they move toward each other, the frequency goes up. And when they move away from each other, the frequency goes down. And I think that's a really easy and helpful thing to remember because, and I want to be clear, frequency and volume are not the same thing. But whatever happens to the frequency is actually also what happens to the volume. Now, this is a totally unrelated thing. It's just like a nice little thing you can think of. You should realize that as something gets farther and farther away from you, you're not going to be able to hear it as well. The volume, or like the energy that's associated with that wave that's getting to you, is decreasing. It gets less loud as it gets farther and farther away from you. That also happens to the frequency, again, for entirely different reasons. It's just that less energy can travel over that far of a distance because it gets lost due to things like friction. The Doppler effect frequency shift is a whole nother ballgame. It's a totally different phenomenon. But whatever happens to the volume, or should I say the amplitude of the wave, happens to its frequency as well. Again, unconnected, but a helpful way to think about it. Notice the same thing is going to happen to the volume of the wave and its frequency. If something is moving towards you like a police siren, it's getting louder and louder and louder and louder and louder. Well, the frequency actually increases also. Again, totally unrelated things. Just a nice, helpful way to think about it. If you look at one of these problems and you think, oh yeah, whatever happening to the frequency, well, that's happening to the volume too. All you have to ask yourself is, in that situation, is the thing going to get louder or less loud? Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now we talked about this in a previous video, and I've already mentioned it like quite a bit here today, but I just want to be totally crystal clear about what it is we mean when we say the apparent frequency increases or decreases, because of course we're talking about different kinds of waves when we're talking about the Doppler effect, specifically sound and light. And so the first question we want to ask here is like, what is the significance in physics of the frequency of a sound wave? Well, the physical significance of the frequency of a sound wave, so the frequency of a sound wave refers to its pitch. Now, of course, we can also ask the question, well, what is the physical significance of the frequency of a light wave? And as we mentioned in the video about the electromagnetic spectrum and about, those sorts of, like the speed of light and sound, the frequency of a light wave refers to its color. These 2 points are very important. Maybe you should write down those questions also, but I just want to go ahead and fix that because that should say physical significance of the frequency. So you absolutely must remember the physical significance of a sound wave is that it refers to its pitch. The physical significance of a light wave's frequency is that it refers to its color. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so I want to just take a second here to talk about light because I think the frequency shift in sound is pretty easy to observe and pretty easy to characterize if you have like any rough background in music whatsoever. And I don't really mean like formal training or anything like that. Like the music class you take at school is enough. You should be able to distinguish low pitch from high pitch, right? Like in music, you all play keyboards, don't you? So like on the left end of the keyboard that you'd be playing with your left hand, you'd be getting those deep sounds. Those are low pitch sounds. And all the way on the right end of a keyboard, you get those really high pitched sort of chimey sounds. Those are high pitch and thus high frequency. Light, on the other hand, it's not as like obvious when you hear something like, oh, that's a low, or I should say, you should see something. Obviously, you don't hear light. It's not as obvious when you see light, like, oh, that's a low frequency light or that's a high frequency light. And so we luckily in the reference table have this handy little chart for the electromagnetic spectrum, which displays all this stuff to us. And so clearly you can see here the higher frequency light rays are things like gamma rays, X rays, and UV rays. Remember, everything on this chart is colloquially referred to as light, at least in our field. And the lower frequency things are things like radio waves, microwaves, and infrared. Notice visible light is kind of right in between. And so sometimes it's helpful to look within this visible light scale itself, obviously, because as human beings, this is only kind of electromagnetic radiation we can sense with our eyes. And if you took earth science, and if you didn't, it's totally fine because I'm going to explain it to you right now. If you took earth science, you might have heard of the Doppler effect in the context of something either called a red shift or a blue shift. Now notice here, the frequency of these light waves is increasing as we go up this way. The Doppler effect, interestingly enough, is actually how we know the universe is expanding. Because when things move away from us, which basically everything is moving away from us because the universe itself is expanding, we see the frequency of the light emitted by those stars and galaxies and other celestial objects, we see it decrease, or in other words, get more red. So this red shift, the shift in the visible light emitted by these stars and galaxies and other things, shift towards the red end of the spectrum is how we know they're moving away from us. Of course, we could have guessed this beforehand, just knowing about the Doppler effect. Hey, if it looks more blue over time, then it's moving towards us. And if it looks more red over time, it's moving away from us. And the fact that the light emitted by basically every single star, galaxy, bouncing off of planets, whatever it is, because all of it over time has been shifting to the red, the only reasonable thing that we can conclude is that every single thing we can see in every single direction is moving away. Well, that's probably a pretty good indication that the universe itself is expanding. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I want to jump back to the sound wave example that I showed you in the beginning, just so we can like put a finer point on it because we've now sort of seen how all of this works. But I just want to make a comment on one little thing, because notice here we say red shift, and this is the one all the way at the end, but we say blue shift, which is the color that's not all the way at the end because we have violet out here. I think violet shift is just like a weird term, and all of these colors here at the end could be vaguely considered like bluish. And so that's just why we called it a blue shift. It is like no disrespect to violet as I put an X through it. But it's just because it's identifiable to most people as like some sort of bluish, at least everything in this sort of range from like 6-ish to, well beyond 7 times 10 to the 14 hertz. We call it a blue shift as opposed to a violet shift. Let's take a look at that video back with the car horn that we watched in the very beginning of today's video. And so as we said here, it's really noticeable for sounds because we hear the sound get higher and higher and higher, or the pitch get higher and higher and higher when the thing moves towards us, and then it gets lower and deeper when it's moving away. And we can see that here in this video. Higher. Lower. So notice it gets higher and lower depending on whether it's moving towards us or away from us. And notice you really hear like a break in the way that the sound is shifted when it's coming right at you, because at the point when the car reaches the observer for a brief second, it's neither moving towards it or away from it. It's right there. So one more time. It's exciting. I found it at the ice cream truck. Here we go. Oh, it's going too fast. Listen. So there you can really hear the difference between when it's coming toward and when it's moving away. The relative motion between the source and the observer causes the pitch of the sound to change. All right, now very quickly before we go here, I just want to take a look at a couple of Regents physics style problems just so we can truly get a sense of exactly how we can apply everything we've seen in this video to answering some questions. So here's the first example. Now, before we get into this example, I just want to point something out. Notice here at the very top of this slide, this problem is labeled as Doppler effect worksheet number 50. Back in the day, when I first started teaching this course, I made a worksheet with a series of Doppler effect problems. That worksheet does not exist anymore. I never use it in class anymore. I did that like 6 or 7 years ago. I have since scaled it back and just put everything in a PowerPoint slide. Basically, you can just totally ignore that label. I really just want you to focus on the question. Speaking of which, this question says the driver of a car hears the siren of an ambulance that is moving away from her. If the actual frequency of the siren is 2000 hertz, the frequency heard by the driver may be. And then they give you a list of answer options. Now, there's so much in this question that's worth paying attention to. I think the first important thing for everybody to recognize is the usage of this phrase, the actual frequency of the siren. You may have noticed in the very beginning of this video, I was taking great pains to really try to emphasize that the Doppler shift is what we can refer to as an apparent shift. The frequency of the sound wave does not actually change. It is just a change that the person observes because of the relative motion between the source and the observer. The actual frequency of the wave does not change. It is only how the frequency of that wave is perceived by the observer due to the relative motion between the source and the observer. That's the deal. And of course, because the problem pretty explicitly says these people are in fact experiencing relative motion, then we know that the Doppler effect is going to be happening here. And now notice they specifically say the frequency heard by the driver. So they're really trying to emphasize in this problem too that this is apparent. Now, it's important to realize if, let's say this is our siren here, oh boy, and this siren is, let's just say, moving to the left of our screen here. If they're moving away from the driver of the car, then that means if the driver of the car is over here, let's just draw the car, oh boy, then the siren, when it was over here, is going to be emitting a wave and then moving away and emitting a wave and then moving away and emitting a wave and then moving away. So the idea is because they're moving away, we see like a stretching of these wave fronts. And so what it appears, at least to the driver, is that the apparent wavelength of these waves is getting larger. Now, remember, it's all about looking at the wave speed equation. According to the equation for the speed of a wave, because the speed is determined by the medium, which in this case is just going to be the air that the sound wave is traveling through, we can see here that the frequency is inversely proportional to the wavelength. And so because this siren is moving away, the apparent wavelength goes up and the apparent frequency goes down. Now, that's an important thing to realize. Now, of course, as I said here earlier when we were talking about this, the same thing that happens to the frequency happens to the volume. And everybody should realize that as this ambulance is getting farther and farther away from the driver of the car of the car is not going to be able to hear it at as loud of a volume. It's going to get lower and lower and lower. And well, as we said, the same thing happens to the frequency. So if the actual frequency here is 2000 hertz, the frequency heard by the driver has to be lower. And notice what choice 2, 3, and 4 have in common is they are not lower than 2000 hertz. Really, if you had no idea about the Doppler effect, you should realize these Regent-style questions are always kind of easy like that because you can really turn it into a game of like which one of these is not like the other. All of the frequencies given in this question, besides choice 1, are either at or over 2000 hertz. And that means that choice 1, by process of elimination, is really the only reasonable answer choice. Now, of course, we can explain the physics behind it. It's moving away, the apparent wavelength increases, so the apparent frequency decreases. But it's important to realize that if you need to bail yourself out. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at another problem. All right, let's take a look at another problem here. This problem says a stationary person makes observations of the periodic waves produced by a moving source. When the wave source recedes from the observer, he observes an apparent increase in the waves. Now, of course, the question here is, well, why are we answering this kind of question? Well, for two reasons. The first reason is I want to show you how they could sort of put a different spin on this question while basically testing the same features of the Doppler effect. The other thing is that it's very important for you to recognize pieces of vocabulary like this. When they say the wave source recedes, what they're saying is that it moves away from the observer. And so when they're telling you here that the wave source recedes from the observer, that's a fancy schmancy way of saying it moves away. And as we said here, when the source moves away from the observer, we see that spreading out of the wave fronts, which makes it seem, notice he observes an apparent increase in the wavelength of the wave. That's a very important thing for everybody to realize. Sometimes they can use some fancy vocabulary here. I think that's an important thing to pay attention to. Take a second to pause this video here and make note of that piece of vocabulary. And when you hit play, we'll take a look at one last problem before we go. Now, very quickly before we take a look at this last problem, I actually just want to bounce back to the problem we just looked at. Because notice, number 50, at least as it's labeled in the slide, and number 52 really are kind of the same kind of question. But I want you to imagine an even more interesting question that we could ask. Notice here, number 50 is asking about the frequency heard by the driver of this car. What if this question, instead of saying what is the frequency heard by the driver of the car, what if the question said, what is the frequency heard by the driver of the ambulance? Again, it's very important for you to remember what it is we're actually talking about. The Doppler effect is the apparent shift in frequency due to the relative motion between the source and the observer. And if the driver of the ambulance is the observer, well, inside of the actual ambulance, the siren is on top, and the driver of the ambulance is always right below the siren. And so in that case, there would be no relative motion between the source and the observer, and that would make the answer choice 2. Really, really important to pay attention to the subtle variations they can put on these questions. Notice here they're asking you about moving away and asking you about the frequency. Here they're asking you about moving away and asking you about the wavelength. Here's a totally different kind of question altogether. It says here a source of waves and an observer are moving relative to each other. The observer will detect a steadily increasing frequency if, and it says he moves toward the source at a constant speed, the source moves away from him at a constant speed, he accelerates toward the source, or the source accelerates away from him. Now, I want you to take a second to pause this video here and think about which answer choices you can immediately eliminate. You should have this broken down then to 2 choices thrown out, 2 choices remain. Once you've narrowed this down to 2 choices, hit play, and we'll wrap this question up. Okay, now I think it should be pointed out here that this kind of question is rare for them to ask in Regents' banks of questions. However, it is important that we take a moment to discuss this. Now, as I mentioned here, you should immediately be able to eliminate answer choices right off the bat, or at least a few. And I think the key piece of information given in the problem is that the observer is detecting a frequency that is increased. And so notice here, I think that should automatically cause you to realize choice 2 and choice 4 are out. And that's because these choices are saying the source and the observer are moving away from each other. And if they move away, as we've just established here with these last 2 questions, that means the frequency goes down. So now we have a choice between choice 1 and choice 3. And the key detail here is that it says here the frequency is steadily increasing. And the only way you get a continuously increasing frequency is due to acceleration. Let's be very, very, very clear about this point. If the source and the observer are moving toward each other at a constant speed, the frequency will shift up to a constant higher value. If they're moving away at a constant speed, the frequency will shift down to a lower but still constant value. The only way you will see an increase or decrease is because of acceleration. And that point is a little confusing, so I'd like us to write that down as our final note for the video. Note, when the source or the observer is moving at a constant speed, the frequency will shift up or down to a constant value. However, when the source or the observer accelerates, the frequency will steadily increase or decrease. Take a second to pause this video here and write that down. When you hit play, we'll wrap it up for today. All right, everybody, so that is the Doppler effect, the apparent shift in frequency due to the relative motion between the source and the observer. Now, of course, I'd like to just take a minute here to comment on the aim for today, because we were talking in the aim, at least, about how the Doppler effect allows us to track the motion of objects. The idea is totally embedded in how a radar gun works. A radar gun makes use of the Doppler effect. So does like Doppler weather radar for weather systems. The idea is a radar gun is basically just like a laser. It shoots an invisible to the human eye light beam at a car. That beam bounces off of the car and then comes back to the radar gun. And because of the motion of the car, at least the relative motion between the car and the police officer who may be shooting the radar gun, the frequency of that reflected beam or those series of reflected beams will change. And due to the shifting of that frequency, using some equations that are really not covered in this course, you can actually calculate the speed of the moving object. It's the same thing with like a storm cloud. If we shoot some sort of like light wave laser beam or radio wave, that's why they call it radar, at a storm cloud, based on the way the frequency changes when it bounces back, we can tell if that storm cloud is moving towards us or away from us. Based on how much the frequency changes, we can tell how fast it's moving. And so that notice has allowed weather professionals to be able to predict with increasing accuracy when storm clouds are going to reach us, when it's going to rain, et cetera, et cetera. The way that the motion of objects is tracked, whether it's planes with radar or whatever, is all about the Doppler effect, the apparent shift in frequency when there is relative motion between the source and the observer. All right, everybody, that is it for today. Hopefully you learned a little something interesting that perhaps you can apply, to a wide variety of things, even some of the stuff that you're learning in shop. And that's it. Have a good one, everybody.